welcome you all to this session of thermodynamics. In the last class, we just introduced the concept of fugacity. So, today we will discuss further on this property fugacity. Well, so if I again continue the discussion in the last class as regarding the introduction of fugacity, let us start again like this, a little repetition of the last class, that the molar Gibbs function dg at constant temperature and pressure can be written from the property relation dg/Tp, that means at constant temperature and pressure, as Vdp. This was told in the last class. Now, for an ideal gas, one can write this as V is RT by P. For an ideal gas, we know V is RT by P. So, when ideal gas equation is used, then we can write this as RT d of ln P at constant temperature. So, this is the relationship for an ideal gas, okay, at constant temperature and pressure dgt. Now, for any other substance which is not an ideal gas, we can write the similar expression instead of pressure here, the similar expression with F as the fugacity. So, this equation itself defines the fugacity. And from this we can tell that we know that any gas which is not an ideal gas at a very low pressure behaves as an ideal gas, which means the limit of F by P, P tends to 0 is equal to 1, which means that this was told in the last class also, that when pressure tends to 0, the gas becomes very much rarefied, then fugacity approaches to pressure. So, therefore, in general we see that fugacity does the same role as done by the pressure in an ideal gas in defining the change of molar Gibbs function at constant temperature and pressure. So, this concept was given last class. Now, we proceed further. Now, if we integrate this equation between 2 points, one is at a reference state P start to any other pressure P at a constant temperature, sorry, not at a constant pressure, I am very sorry, it is at a constant temperature only, at constant temperature, I am sorry, at constant temperature, then we get RT d ln F, well, is this at constant temperature from F star to F. F star represent the fugacity at the reference state at T and P star. Then we can write G is equal to G star plus RT ln F by F star. This is one very important relationship. And as we know, we have seen earlier from the study of multi-component system that the molar Gibbs function of any component is equal to its thermodynamic potential. So, mu, as we define the thermodynamic potential, mu star plus RT ln thermodynamic potential, which came in relation to the multi-component system, but here we are using a single component system. Now, from here we can write, we will derive one important equation, G minus G star is RT ln F by F star. Now, this G minus G star is the integration of dg at constant temperature from P star to P, which we can write as Vdp, because this relationship is valid for any gas which may not be ideal. So, therefore, here we can also write equals to Vdp from the reference state P star to P. So, if we do this integration, this Vdp, then what we do? But we cannot do the integration, sorry, until and unless we know V as a function of P. So, before that we write RT, now rather we write this ln F, if equate this is equal to this, RT ln F minus RT ln F star equals to P star to P star to P Vdp. Now, we can write another equation this way, RT ln P minus RT ln P star is nothing but RT integration of dP by P from P star. That means I just write an equation like that, RT dP by P gives ln P from P star to P. So therefore this is equal to this. That means I use this equation. This is an identity. RT integral dP by P, P star to P is RT ln P minus RT ln P star. So if I subtract this one from this, I get RT ln F by P is equal to RT ln F star by P star plus integral P star to P. What will be there? V minus RT by P dP. Now if I consider P star very small, that means the reference state is such that the P star, that the pressure of the reference state approaches 0. What we know that F star approaches P star, which means F star by P star 1, so ln of this becomes 0. So we can write an equation that ln now F by P, RT we divide this side, is equal to P star to P integration now V by RT. R is the universal gas constant, V by RT minus 1 by P, 1 by P dP. So this is a very important relationship regarding the fugacity, important expression of fugacity in terms of pressure and volume. And for any real gas, if we can know the pressure and volume relationship from its equation of state, we can find out the expression for the fugacity. This equation can also be written in another form. Let me tell you that this equation can also be written in another form. Let me tell you that ln, this is another form of this equation, ln, little bit algebra is there in this part of this class, that P star to P, which we have done, V by RT minus 1 by P dP. Okay. Now we know that for a real gas, we can define the equation of state in terms of a compressibility function Z or compressibility factor Z, compressibility factor Z, which takes care of the non-ideality of the gases. That means for an ideal gas, Z is equal to 1. So if you define PV is equal to ZRT as the equation of state for any real gas, then this can be written as, you see, V by RT is V by RT, here is V by RT is Z by P. So therefore we can write P star by P into Z minus 1. So dP by P can be written as ln dP, because V by RT is Z by P minus 1 by P. So Z minus 1 dP by P has been written as, this is another useful, the same expression in another useful form. Now let us have some example before proceeding further. Let us find out the expression of fugacity, find out an example, find out the expression of fugacity, the expression of fugacity, the expression of fugacity. Let us have this example, fugacity F in case of a van der Waals gas, of a van der Waals gas, whose equation of state is as follows. Let us consider the equation of state of a van der Waals gas, and we will find out this, the van der Waals equation of state. This is given, P is equal to RT, you know the van der Waals equation, minus A by V square, where A and B are the parametric constant in the van der Waals equation of state. Now how to find out this? Now we start from this, dGT is V dPt. We start, therefore we can write dGT is RT ln F by, so you write from here dG at constant T is equal to what? RT ln, this is integral, if we make this integration from P star to P, we get RT ln F by f star, which equals to integration of p star p v dp, which we already used earlier. I just show you that this one, g minus g star RT ln f by s f star v. This is nothing but dg at constant temperature from p star to p. Now here if we equate this, we get RT ln f minus RT ln f star. Now this VDP here we have to make a tactful substitution, or we have to reorganize this thing in a way that we can integrate it properly, because V is given explicitly, not V is explicitly in terms of P, so that we can integrate it with the variable dP. That means integration is made with respect to dP. So V is not explicitly given to P, so that we can substitute and integrate. So what we do instead, we write this P star VDP we can write as T d of PV minus PdV. Well, and this sorry, and this can be written as integral d of PV from P star to P. That means we can write this as PV minus P star V star. That means if we integrate this part. So V star is the corresponding volume at the reference state P star, and V is the corresponding volume at the state P. So PV minus P star V star. These are all done at constant temperature. These are all done at constant temperature. These are all done at constant temperature. Then minus PdV minus P star to P PdV. Therefore, we can write now RT ln f, little algebra is there, minus RT ln f star equals to PV minus P star V star. Now I just substitute P explicitly in terms of V, which is possible from this type of equation of state, P star by 2P. Then what is this? P is RT V minus B minus A by V square dV. And if we write it or integrate it in the next step, if you write, you see that RT V minus B is ln V minus B and P to P star. So the minus is there. So therefore we can first write RT ln, okay, V star minus B minus RT ln V minus B, RT ln V minus B, RT ln V star minus B minus, now this is minus minus plus A by V square, this minus, so plus A by V star minus A by V. All right. So A by V square integration is minus A by V. So if you take the limit, it will be like that, where again I am telling V star is the volume when P is P star and V is the volume when P is P. All right. Now if we use certain relationship, now like this, as P star tends to 0, the reference state pressure is very low, then V star tends to infinity. And one thing is that F star by P star tends to 1. All right, F star by P star tends to 1. So therefore, what you do now, if you just write this, well, from here you can see that now, all right, now here if you just RT ln F is equal to RT ln, now I just substitute, you just make like this, minus RT ln P star plus RT ln P star, you understand? So plus PV minus P star V star. That means I keep this RT ln F star here, RT ln F star here, I take this on the right hand side, RT ln F, RT ln F star this side, RT ln F star. So 1 minus RT ln P star is there. Okay, so plus RT ln P star I will have to make, which I make it here, RT ln P star into V star minus B. all right. Then I use minus, then I write the rest part RT ln V minus B plus A by V star minus A by V. This is okay. Now, in the next, now our next task will be like this. Now ln RT ln V minus B, now RT. Now RT we will just substitute, just divide from both the sides. So we get ln F is ln F star by P star plus PV by RT minus okay, P star V star by RT plus ln P star V star minus B minus RT ln V minus B plus A by RT V star, okay, minus A by RT V. All right. Now, we will use this equation of state in this fashion, that the equation of state can be written as PV by RT is equal minus 1 is equal to V by V minus B minus A by RT V minus 1. How do I get it? Just from the first slide, if you see that the here, yes, not from the first, here, that P is equal to RT V minus P into V minus B, that means PV by RT, rather I just multiplied with V and RT. So you multiplied V, that means if you see that here, well, PV by RT, that means A by RT V is multiplied minus 1. So from this equation of state I can write this, so that PV by RT minus 1 becomes equals to V by V minus B minus A. Now if I take this, that means B by V minus B minus A by RT V. All right. Now what I do, you see, F star, now if P star is very small, that P star, now if I take P star tending to 0 and V star automatically tending to infinity, so what we do? So P star tending to 0 means this is ln 1 0. Now when P star tending to 0 and V star tending to 1, at this reference state the gas behaves like an ideal gas, that means P star V star is RT. That means P star V star by RT equals to 1. All right, that means we can write ln F is equal to PV by RT minus 1. So PV by RT minus 1 is again this one, that is B by V minus B minus A by RTV. All right. Now here again we see that RT ln V minus B. Okay. Now ln P star V star minus B. So this also can be shown equal to, now if I write this ln P star V star minus B from the equation of state, something here I do. That equation of state, if you remember, P is equal to RT V minus B minus A by V square. Okay. Then P into V minus B, if I multiply it, is equal to RT minus A into V minus B by V square. Now when P tends to 0, that means if I just substitute P star, for example, that is P star is 0, P star tends to 0, then V star minus B is RT minus A V star minus B divided by V star square. So here you see the terms are getting 0 because denominator is V star, it is 0. That means P star into V star minus B is RT. That means this part I can write RT plus ln RT minus this RT is okay. What I have done, RT ln if, so there will be no RT because I have multiplied divided by RT, so RT is not there, I am sorry, ln V minus B. All right. Now again you see V star tends to infinity, this term is 0, so minus A by RTV, so this remaining term. So ultimately we get ln if these two things are taken together, RT by V minus B, then this term is B by V minus B, and this two term is minus twice a RTV. This is one of the very important expression, that the fugacity F, finally fugacity F for an van der Waals gas becomes equal to this one, F is equal to ln RT V minus B. This is the expression of fugacity for van der Waals gas, van der Waals gas. Now we will go for a multi-component system. We will now go for a how to define fugacity for a multi-component system. Now multi-component system, the fugacity of multi-component system, fugacity in multi-component system. Now for a multi-component system, the fugacity is defined like this, that for a multi-component system we know that the partial molar, if we define in terms of the partial molar Gibbs function at constant temperature, is defined as RTD ln Fi. Fi is the fugacity of the ith component. So this is the definition of the fugacity of an ith component in a mixture of multi-component system, where Gi bar is the partial molar Gibbs function of the component and Fi is the fugacity of the ith component. So this is the definition, and here also the limit we can write Fi by the pressure of the component in the mixture, that means its mole fraction times the total pressure. This tends to 1 when the total pressure tends to 0. Don't make a mistake that XIP or the partial pressure 0, this is wrong. When the total pressure goes to 0, then this Fi behaves as the partial pressure, that means XIP of the component. Why? Because it is very simple, that you can understand that in a mixture of gas, if one component has a marginal amount, that means a gas, a real gas, which component whose amount is very marginal in a mixture, or a very dilute mixture of a real gas in other gases, does not make the mixture as an ideal gas. You understand? Until and unless the total pressure approaches 0. That means in a mixture of real gases, one real gas may have a very marginal quantity. That means it is infinitely diluted with that particular real gas. That means the partial pressure of that gas is approaching 0, but that does not mean the mixture will behave as an ideal gas. So therefore, here very important thing is that P tends to 0, not XIP tends to 0. This is wrong. So this is the basic concept of the basic concept of the fugacity of an ith component in a multi-component system, and we can find out the expression for fugacity in a multi-component system in the similar way as we have done for the single component, as we have done for a single component system. How we can do it? We can integrate this equation and can write this way: Gi bar minus Gi bar star, where this is a reference state, is RT, if we integrate this, ln Fi star, that is the reference state, and that equates to similarly Vi dP. That means the partial volume. Instead of the molar volume, it is the partial molar volume, which means that dGi bar at constant T is nothing but Vi bar dP. That is our relationship. So therefore, if I integrate that, I get this thing. So in the exactly similar way, I can do Fi, okay, is equal to RT ln Fi star plus integration of P star P Vi dP bar. That means the partial molar volume of the ith component in the mixture. And in a similar way, I can write RT ln, instead of Fi, I can write XIP is equal to RT ln XIP star is equal to just a mathematical identity here. That means it will be dP by P from XIP to XIP star. That means here you see the connotations of a thing that Fi is the fugacity of the ith component at a state P, then Fi star is the fugacity of the ith component at the reference state P, and there it is integration of Vi bar, where this is the partial molar volume of the ith component. Now here I am giving an identity where Xi P is the partial pressure of the component whose mole fraction is Xi, and Xi P star is the partial pressure of the component I when the total pressure is at the reference state, that means P star. So we can write, that means this is a mathematical identity. The similar way we did for the single component, we are doing for the multi-component system also. Then we just subtract and we get RT ln Fi by Xi P, okay, is equal to RT ln Fi star by Xi P star, well, plus P star by P, and your RT, that means here has to be RT, that means Vi bar minus RT by P dP. That means if we, now here Fi star when Xi P star, that we have shown, when Xi P star is very small, then what happens? Then Fi star is P, okay. So Fi star is Pi. When P star is going to 0, then what is the fugacity? Here P star going to 0, then fugacity is equal to the Xi P star. That means this is 1, so this. That means the reference state, when the reference state is very what I call, reference state is at a very low pressure. So therefore we can write ln Fi by Xi P is equal to, okay, this is P star by P into Vi minus RT by P dP. This is a very same relationship, similar relationship as we developed for the, I show you just now we have developed for a component, for a single component. There is a molar volume, and difference is this is the component fugacity for the component, for the pure component it is the fugacity of the ith component in a mixture. This is the partial molar volume of the mixture of the component I in that mixture, okay. So this is multi-component, this definition of fugacity in the multi-component system. Now we will derive the dependence of fugacity with pressure and temperature. Dependence of fugacity F with pressure P, temperature T, and mole fraction S. We will define in case of a multi-component system and mole fraction S, okay. Now we see that where from we start. Now we start from here. We know that the definition of G from the very basic is H minus Ts for a single component system. Molar gives function H. So dG is dH minus d of Ts, which equals to dH minus TdS minus SDT. Again I am doing this, has been done several times. dH is du plus PdV plus VdP minus TdS minus SDT, and you know du plus PdV is dTs, TdS, so TdS cancels, so VdP minus SDT. So this is our starting point definition. Now for a multi-component system, as we have already studied, we know that the same expression, same relationship holds good if we just substitute molar Gibbs function by the partial molar properties. That means in case partial molar Gibbs function, partial molar property of the ith component. That means for a pure component this was partial molar Gibbs function, molar volume, molar entropy. Here partial molar Gibbs function of ith component, partial molar volume of ith component, partial molar entropy of ith component. So we start from here. So now here from we see del Gi, that means the partial molar volume bar, by del P at constant temperature will be nothing but Vi bar, del Gi del P. Now again we see here, we have already noticed this expression, we have already I have already dealt with this expression. What is this? This is by definition RT d ln Fi. This was the definition of the fugacity. Now here these are all at constant temperature. Now here if I divide it by dpt, that means if divided by a change in pressure at constant temperature dp at T, then we can write this thing, change of pressure at constant temperature if I just divide. That means in other way, this integration of del Gi bar del P at constant T can be written as R del ln Fi del P, and this is at constant T, constant temperature, constant T. Well, so that now if I use this, equate this with this, then we can get del ln Fi del P is equal to Vi bar by RT. So this is the most important relation, that means this is the relationship of Fi with pressure. That means dependence of F with P is del ln Fi del P is Pi bar by RT. Now for a pure component the expression will be, for a pure component, the counterpart will be del, well, the counterpart will be del ln F, del ln F, that means the fugacity of the component del P is simply Vi. Sometimes I write 0 on the subscript, which means the for the ith component as a pure component. That means if we compare these two, we should write this way, where Vi bar is the partial molar volume of the ith component at that mixture, and Vio is the partial molar volume, rather partial molar volume or simply molar volume, I will not tell partial, molar volume of the component I as the pure component at that same pressure and temperature. So del ln Fp is Vio by T. This is for a pure component I itself when exists as a pure component. Okay, so this is for the pure component. Now we come to the dependence of temperature. For the dependence of temperature, we start from here. We have already seen that Gi bar minus Gi star, that means the reference state, the difference between this partial molar Gibbs function of the ith component, this is equal to RT ln Fi by Fi star. Alright. Now if I differentiate this with temperature at constant pressure, then what I will get? Del Gi del T at constant pressure minus del Gi star del T at constant pressure is equal to, now if I differentiate this at constant pressure, then what it will be at constant pressure, the temperature, so ln Fi by Fi star, R will be there, then plus RT, then del ln Fi by del T at constant pressure minus del, what is that, ln Fi star by del T at constant pressure. Alright. Now if we go back to our this definition, del Gi Vi dP minus this dt, then what is del Gi del T? That means here I write again del Gi, what is del Gi, that is the del T, that is the with at constant pressure, the partial differential with respect to T at constant pressure is minus Si bar. So these are all known things we did earlier, that this is the relationship, property relationship. Therefore del Gi bar, that means del T, that means the partial differential of partial molar Gibbs function of ith component with temperature at constant pressure is nothing but minus Si bar. Si bar is the partial molar entropy of the ith component. So therefore minus Si bar. So this will be minus Si bar minus Si star bar, that means the partial molar entropy at the reference state star, and this is equal to R ln Fi by Fi star. So what is that value of Fi by Fi star? R ln Fi star, I can write from this equation again Gi bar by T minus Gi Gi star bar by T, Gi by T, well, minus Gi star by T, all right, plus, now you see Fy star is a constant, that is a fugacity at the reference state, so we can neglect this, that means we can make this to 0. So therefore, we get plus RT del ln Fi del T at constant pressure. Now if we just multiply T on this side, what we get? We get, if you just multiply this side and this take this side, Gi star, multiply T on both this side, Gi star minus T Si star minus Gi, just little algebraic manipulation, minus T Si bar is equal to RT square, because we have multiplied by T into del ln Fi by del T at constant pressure. Now Gi minus Ts, what is that? By definition, Gi is equal to Hi. You know the definition, G is equal to H minus Ts, and this holds good. We know, now here we do that, we know the definition of G is molar Gibbs function for a pure component S. So therefore, for a multi-component system, this will be, that means this molar properties will be replaced by the partial molar properties. Okay. So if so this becomes Hi bar star and this becomes Hi. So therefore, we can write del ln Fi del T at constant pressure is equal to Hi star minus Hi, all with bar, Hi bar star minus Hi bar divided by RT square. So this is the required expression for the dependence of fugacity with temperature. This is the dependence of fugacity with temperature. Now, for a pure, what will happen for a pure component? So therefore, we will repeat for a pure component. For a pure component, rather we write here, for a pure component, here you will write, for a pure component, this will be del ln F divided by del T. That means for a pure component, where I will denote FiO. That means the ith component, when it exists as a pure component, then what will be? Hi star minus Hi divided by RT square. These are the molar enthalpy of the pure component. So this I give as the 0. That means, it means that when ith component exists as a pure component at the same state of the mixture, so del T ln Fi 0 is Hi 0 star minus Hi 0 by RT square. So this is valid for the pure component. Now I will come to the mole fraction. Okay. So dependence with mole fraction. Here I will start with a binary system. Here I will start with a binary system. All right. I will start with a binary system. What is that? Two systems, 1 and 2. We know for a binary system, we have already deduced this equation, n1 d mu 1 plus n2 d mu 2 is 0, where n1 is the number of moles, consider a mixture of 1 and 2 with n1 and n2. So n is the total number of moles, n1 plus n2. And mu 1, mu 2 are the chemical potentials of component 1 and 2. So this equation we know. And we also know, just now we have learned that d mu 1 is equal to RT d ln F1 in terms of the fugacity. D mu 2 is RT d ln F2. Well, d mu 1 is nothing but dg1 bar and d mu 2 is nothing but dg2 bar. So this we know. So RT d ln F2. So if you now substitute this, then we get n1 RT d, well, ln F1 plus n2 RT d ln F2 is equal to 0. Now we can divide both the sides by either nRT2 or nRT1. Results will be same. You can do it. Let me do it by dividing nRT2. So N1 by N will be x1 mole fraction and RT, sorry, yes, it is all right, nRT, sorry, I am sorry, it will be either N2RT or N1RT, I am sorry, not T1T2. Result will be same, I am sorry. Let me divide it by N2RT. N2RT. You can divide by N1RT also, the result will be same. So now you see, I am sorry, I am extremely sorry, nRT, I am sorry. We divide by nRT, nRT dx2, nRT dx2, I am sorry, I am extremely sorry, either nRT dx1 or by nRT dx2, not N2RT, not N, this is, I am sorry extremely, so either nRT dx1 or nRT dx2. So I divide by nRT dx2. So it is x1. Now dx2 at what I do? This is defined at constant temperature and pressure. Only this mole fraction is changing. All right. So that RT is cancelled out. So N1 by Nx, you can write this ln F1 by del x2 at constant temperature and pressure. That means mathematically this is at constant temperature and pressure. Constant temperature. That means either you multiply with this, sorry, or you multiply it with dx2 at constant temperature. I am multiplying with nRT dx2. Then what will be that x2 and del ln F2 del x2 at constant temperature and pressure is 0. Now you know that x1 plus x2 is 1. Why? N is equal to n1 plus n2. Divided by n, 1 is x1 plus x2. So therefore, dx1 is minus dx2. So therefore, if I take this minus at this side, then I can write now x1 del ln F1 del x2 is equal to, is a very important relation, x2 del ln F2 del x2, all are at constant temperature and pressure. And we can take this x1 inside, that means del, sorry, now it will be del x1 by x1 and del x2, because del x2 is minus del x1, so that it has gone that side, so this is equal to this. Now if I take del x1 by x1, this can be written as del ln F1 by del ln x1 at constant temperature and pressure is equal to del of ln F2 divided by del of ln x2 at constant temperature and pressure. And it can be written when the pressure tends to 0, very low pressure, these fugacities can be expressed as partial pressures of the component del ln P del ln x1. This is another form at very low pressure, this dependence of the partial pressures with the mole fractions del ln x2 at constant temperature and pressure. And this equation is very important equation and known as Duhem-Margulis equation, M-A-R-G-U-L-E-S, Duhem-Margulis equation. This equation is an important equation. Well, so these are the two forms for the dependence of fugacity with the mole fractions. Fugacity is a partial pressure. When the pressure tends to 0, this equals to the partial pressure for a multi-component system, for a component in a multi-component system. All right. Now we will go to another section, that is an ideal solution. What is an ideal? Now after discussing all these things, we will come to ideal solution. What is an ideal solution? What is an ideal solution? How do you define an ideal solution? Now we will come to an ideal solution. Now what is a solution? First of all, you will have to know what is a solution. A solution means a mixture of many components. Mixture of many components are known as solution. That may be in solid state, that may be in liquid state, that may be in gas state. that means a mixture of real gases is a solution. A mixture of many liquids we can tell at solution. Even the mixture of many solids we can tell at solution. So in solutions is a mixture of many components, and a solution is told as an ideal solution when this expression is valid. When this expression is valid, this is the expression which defines an ideal solution. Ideal solution means the fugacity of any component in that solution equals to the fugacity of that component at the that component at pure state. That means that component as a pure component at the same state of the solution multiplied by the mole fraction. Fi is Fi0 xi. That means in an ideal solution the fugacity of any component equals to the fugacity of that component as a pure component at the same temperature and pressure and the aggregation of the solution. That means the same state of the solution times the mole fractions. So this simple relationship holds good for ideal solution, or other way we can tell, when for each and every component in a solution this equation is valid, we tell this solution as an ideal solution. Now with this as an hypothesis of an ideal solution, we have certain corollaries of ideal solution. That is, the volume change in mixing is 0. Volume change in an ideal solution, in an ideal solution, in an ideal solution, or in preparing an ideal solution, in preparing an ideal solution is equal to 0. How do I prove it? Let us consider an ideal solution is made up of N1, N2 like that n number of components, and each has a partial molar volume in the solution, that means mixture as Vi1, V1, V2 dot 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 Vr. So therefore the total volume of the solution V solution is equal to the sigma of Ni Vi, I goes to Vi bar 1 to R. You know that thing, we have already discussed that the extensive property of a solution is equal to sum of the product of the number of moles times the partial molar property of that property which you are finding on, for example volume. So product of the sum of the products of this Ni Vi. So before solution total volume V is equal to sigma of Ni into Vi0, I1 to R. So therefore change delta V, change in the volume to make the solution is sigma Ni into Vi minus Vi0. Now this is 0. How to prove this is 0? Very simple. We know now, we have already derived these two properties. If you just see that just now we have derived this thing, just now we have derived this thing, okay. I just show you just now for this, just now we have derived the AS, it has come, just now we have derived. What we have derived? Del L ln Fi del P is this, and del N Fi 0, that means for a pure component Vi 0. That means if I write it now, it will be like this. Let me write it now. Del ln Fi del P is Vi bar by RT. Just now I have done it. And for a pure component, del ln Fi 0, that means when the component I is at the pure, as a state of pure component at the same state of the mixture, is equal to Vi 0 by RT. This is at the obviously same temperature. Always when I differentiate it with pressure, here is the same temperature. Now if I subtract this from this, then what we get? We get del ln Fi, very simple, Fi 0, this thing, rather this first bracket you make, this thing divided by del P at constant temperature is equal to, then you just Vi bar minus Vi0 by RT. Now you see Fi by Fi0 is Xi, which is constant at constant composition. So therefore this is constant, so this is 0, so therefore this is 0. So therefore del V solution is 0. In the similar way, we can tell that the change in enthalpy in an ideal solution is 0. Change in enthalpy in an ideal solution is 0. In an ideal solution is 0. How we should tell it? Ideal solution is 0. In the similar way, we can tell that delta H in an ideal solution is similarly sigma Ni into, what is that? Into Hi bar minus Hi 0. Obviously, Ni Hi bar is the total enthalpy of the mixture. Ni HiO is the enthalpy of all the pure components, total enthalpy. So enthalpy change of solution. And also we can write out in the similar fashion, if we see this expression earlier, that these two, del ln Fi del T at constant pressure is this for a multi-component system, ith component present in a multi-component system and at its pure state, which we have defined earlier. We can write, you also see, you do it at your home, everything line by line, I will not do in the class. So del T, okay, this is at constant pressure, it becomes is equal to, in the similar way we did for the volume change RT square. Against this is 0, because Fi by Fi 0 by the definition of the ideal solution is Xi. So therefore which is constant for constant composition. So therefore this is 0. So therefore delta H solution is also 0. So change in the enthalpy of the solution is also 0. Now after this we will come to define dilute solutions. Now so far we have told about the ideal solutions. Now what are ideal solutions? In practice you must know that the mixture of real gases at low pressures is an ideal solution, which means the mixture of ideal gases are ideal solutions. Again, the mixture of non-electrolyte solutions, liquid solutions at high dilutions behaves as an ideal solution. What is non-electrolyte solution? A non-electrolyte solution means a solution of liquids, non-electrolyte liquid solutions, where all the components exist as uncharged species rather than charged ions. Alright? And these non-electrolyte solutions at high dilution, what is meant by high dilution? That means with respect to a component it is diluted. That means one component is in a very meager amount. So that is known as a high dilute solution. This behaves as an ideal solution. Okay, so these are the examples of ideal solution. Now I come dilute solution. In continuation to, what is a dilute solution? Dilute solution means if there is a mixture of many components in a solution, 1, 2, 3, 4, 5, like that, number of solution, and if one of the components, say for example 1, predominates by its amount and other components are very meager in its amount, then this is known as a dilute solution. And this solution behaves as an ideal solution with respect to the solutes. That means I can write for any of these 2, 3, 4, F2 is F20 X2. And this is expressed as F2 as a constant, because this is constant, this is the fugacity of the pure component of any of these 2, 3, 4 at the same state of the mixture X2. Okay. So this is the definition of the, this is the definition or this is the law that is valid for all these components which are meager amount. Now in a dilute solution where one component dominates, this is known as solvent, and the components which are dilute, that means which are existing in by meager amount, are known as solute. So for any solute, this is the equation, because they behave as an ideal equation. And in fact, this was stated in terms of the partial pressure. This is an empirical equation, empirical law, empirical found from experiments, empirical law, and it was found by Henry and known as Henry's law. So Henry's law states that the partial pressure, in terms of the partial pressure or partial vapor pressure in a liquid solution of a component which is a solute in a dilute solution is proportional to its mole fraction. Okay. With this we can prove the similar thing for the solvent. How we can prove? Now if you write the equation, if you remember, just now we have derived del ln F1 by del ln X1. So, that we have just derived at constant temperature and pressure is equal to del ln F2 divided by del ln X2. Just now we have derived at constant temperature and pressure. Just now we have derived this. If you remember, just now we have derived this expression, that this one X1 this thing, and after that we just now we have derived del ln F1 X1 del ln F2 X2. Then what we can write, that ln F2, so F2 is Kx2. So, del ln F2 is ln K plus ln X2. So, K is constant 0. This K is F2 0. Okay, for the solute. Already you know, behaving as an ideal gas, that is the Henry's law. So, del n, so therefore, ln F2 by X2 is 1. So, therefore, what we get, F2 is ln F2. So, del ln F2 by del ln X1. So, the ln F2 by ln X2 is 1. So, rather we can write this way, ln F2 is ln, or we can write del ln F2, this will be better, del ln X2. So, del ln F2 by del ln X2 is 1. So, if we write, this is at constant Tp, this is at constant Tp. If we write this as 1, okay, so del ln F1 del ln X1 1, that means we can write integration of d ln F1, that means if we integrate this is equal to integration of d ln X1, alright. That means this is equal to 1, so del ln F1 I integrate this from what? From X1 is 1 to X1, and X1 1 means F1 0 pure state to F1, which tells that ln F1 by F1 0 is ln X1, which means F1 is F1 0 into X1. And therefore, we see that for the solute also we have the same type of equation which is valid for the solvent also, sorry, we have the same type of equation which is valid for the solute. And if this solution is a liquid solution which are in equilibrium with its vapor, then F1 can be written as the corresponding partial pressure, and F10 is P10. So, we can write P1 is P10x, and this is known as Raoult's law. This is known as Raoult's law. So, therefore, we see if we compare the Raoult's law and the Henry's law, then we see that whether when Henry's law is valid for a solute, the Raoult's law is valid for a solvent. So, this is Raoult's law for a solute, this is for the solvent, and P2 is P2 0 into X, P3 is P3 0 into X. These are for, this is for solvent, and this is for solute, and this is the Henry's law. Henry's law. Whether when Henry's law is valid for the solute, the similar law is valid for the solvent and is known as Raoult's law. These two laws are very important in dealing with the solutions or mixture of components, but dilute solutions. Mind it that this is valid for dilute solutions, where Henry's law is obeyed by the solutes whose amount is very less, and the Raoult's law is the law obeyed by the solvent. But the law is same, that the fugacity of any component equals to the fugacity of the pure component times its mole fraction. Okay. Thank you.